In the golden age of steam, the Union Pacific Big Boy stood as the largest, most powerful locomotive ever built, the absolute apex of the steam era. But a secret experiment was being engineered to make it obsolete. When the first Union Pacific Big Boy, number 4000, rolled into Omaha on September 4, 1941, it drew crowds and headlines. Here was a locomotive that seemed to defy limits, longer than a city block, weighing over 1 million pounds with its tender, and built to haul 3,600-ton trains up the Wasatch Mountains without help. That autumn, as the Big Boy thundered into revenue service, it was hailed as the ultimate answer to the railroad's steepest challenge. But inside Union Pacific's engineering offices, the mood was already restless. The Big Boy's arrival was not treated as a final victory, but as a benchmark, a measuring stick for what still needed to be achieved. On the surface, the Big Boy stood for unstoppable progress, the last word in steam. Yet the railroad's Department of Research and Mechanical Standards had already begun questioning whether even this giant could keep up with the demands of wartime freight and the rising cost of coal and water. Their calculations showed that the very power that made the Big Boy famous also brought heavy fuel consumption and a constant need for servicing. Each climb up the Wasatch burned through 28 tons of coal and 24,000 gallons of water in a single hour. The machine's 4884 wheel arrangement delivered the required 135,000 pounds of tractive effort, but it was clear to the engineers that this was as far as traditional steam could go. So while the public celebrated the Big Boy as an icon, Union Pacific quietly began searching for something beyond it. The story of the Big Boy is not just one of triumph, but of succession. Its greatest achievement, mastering the mountain grades, was also the moment its designers started looking for the next leap forward. Success and the urge for replacement overlapped in the same breath, setting the stage for a new experiment that would try and fail to leave the legend behind. The Wasatch route between Ogden and Green River was more than a stretch of railroad. It was a proving ground that exposed every weakness in a locomotive's design. Over 176 miles, the track climbed out of the Utah Basin, winding upward through mountain passes where the air thinned and the grade stiffened to 1.14%. For Union Pacific's operating departments, this was not just a question of horsepower. It was a daily struggle to move 3,600-ton trains over a landscape that punished inefficiency and multiplied every logistical headache. On paper, the Big Boy's 4884 wheel arrangement and 135,000 pounds of tractive effort promised a single-engine solution. In practice, the reality was more complicated. Even a locomotive of this scale needed vast amounts of coal and water. 28 tons of coal and 24,000 gallons of water could disappear in just 1 hour of hard climbing. The route's arid stretches meant water stops were few and far between, forcing the railroad to maintain a string of supply points and to dispatch extra tenders when conditions demanded it. Moving a heavy freight train up the Wasatch rarely meant one locomotive in a straight run. The grades forced the use of helper engines, each one adding complexity to the timetable and risk to the schedule. Coordinating multiple crews, staging locomotives at sidings, and synchronizing their starts and stops turned what should have been a simple haul into a rolling systems problem. Every helper added cost and delay, but leaving them out risked stalling halfway up the climb. Reciprocating steam power, for all its brute force, came with a steep price. Thermal efficiency barely reached 6%, and most of the energy in the coal went up the stack as wasted heat. Every trip through the mountains was a balancing act between speed, power, and resource consumption. The railroad's managers watched the numbers pile up: coal bills, water bills, overtime for crews, and understood that even the Big Boy represented the edge of what could be done with steam. This relentless operating burden made radical ideas seem not just attractive, but necessary. The search for a locomotive that could conquer the Wasatch without helpers without endless coal and water stops, became an obsession inside Union Pacific's offices. The mountains set the terms. Every experiment that followed would have to answer to the reality of the Wasatch grades, where theory met the hard facts of the timetable and the ledger. Union Pacific's search for a better mountain locomotive turned from theory to hardware in late 1938, when the railroad and General Electric formalized an ambitious partnership. The challenge was clear: build a machine that could outclass the big boy not just in size, but in efficiency, smoothness, and raw, unbroken power. This was not a publicity stunt or a side project. For both companies, the steam turbine electric was a wager on the future of heavy rail. By December, the Erie, Pennsylvania plant delivered two prototypes, UP1 and UP2. These were not repurposed steam engines with a new twist, but purpose-built machines that embodied the boldest engineering hopes of their era. Each unit housed a water tube boiler running at pressures between 1,500 and 1,600 pounds per square inch, a level that pushed the limits of contemporary materials and safety practice. Inside, instead of pistons, a single stage axial flow turbine spun at a dizzying 12,500 revolutions per minute. That turbine drove a generator, which in turn fed 6 traction motors spread across a 2cc two-wheel arrangement. The result was a locomotive that, at least on paper, could deliver 2,500 horsepower per unit, 5,000 horsepower when the pair worked together. The design philosophy was radical. Where the big boy's pistons hammered out their power with each stroke, the turbine delivered a constant, almost silent surge of torque. There was no pounding, no reciprocating mass slamming back and forth, just a smooth, uninterrupted flow of energy from boiler to wheels. This promised a quieter ride, less track wear, and the ability to run at speeds that reciprocating steam could only dream about. Engineers spoke in terms of potential. A 12-car Pullman can consist up a 2.2% grade, or a freight train that could finally conquer the Wasatch without helpers, without the water stops that had defined railroad timetables for generations. The arrival of UP1 and UP2 in Omaha on April 4, 1939, was loaded with expectation. Here at last was a machine that seemed to leapfrog the old limitations. The turbine's high-pressure boiler and generator chain represented a new way of thinking about rail power. Union Pacific's mechanical staff and GE's turbine specialists worked side by side, poring over test data, fine-tuning controls, and watching for the smallest sign of breakthrough or trouble. The stakes were high, but so was the optimism. If these machines could deliver on their promise, high speed, high power, and far less water burned away as waste, they would not just match the big boy, they would render it obsolete. For a moment, it looked as if the age of piston-driven giants might truly be ending. The turbine's smoothness, its power at high revolutions per minute, and its ability to convert steam into electricity. These were the qualities that Union Pacific and General Electric believed could finally solve the mountain problem. The experiment was underway, and the world of American railroading was watching, waiting to see if the future had arrived in the form of two gleaming, unconventional locomotives. The first 60 days of turbine electric operation were supposed to prove that Union Pacific and General Electric had found the future of railroading. Instead, they delivered a lesson in the difference between engineering promise and railroad reality. The two prototype units, UP1 and UP2, rolled out for mainline testing in the spring of 1939, facing the same punishing grades and tight schedules that had defined the big boy's trial by fire. On paper, the turbines offered 5,000 horsepower, smooth torque, and the possibility of running hundreds of miles without a water stop. In practice, the experiment quickly turned into a rescue operation. Breakdowns began almost immediately. Bearings critical to the high-speed turbine's smooth operation showed signs of abnormal wear after only a handful of runs. Maintenance crews found themselves pulling apart hot machinery on sidings, hunting for the source of new grinding noises and vibration. The water tube boiler, designed for pressures up to 1,600 pounds per square inch, developed leaks and suffered from tube fatigue that forced repeated shutdowns. Each time a turbine stalled on the main line, a conventional steam locomotive had to be dispatched to pull the stranded train to the nearest siding. These were not rare events. Test logs from the period record multiple instances where the supposed replacement for the big boy needed to be hauled home by the very technology it was meant to surpass. The turbines were also sent east to the New York Central for cold weather testing, where a new set of problems emerged. The condensing system, intended to recycle up to 90% of the exhaust steam, struggled in low temperatures. Seal leaks and corrosion in the condenser tubes led to water loss and forced the locomotives to take on fresh water more often than planned. Instead of running hundreds of miles without a refill, the turbines found themselves stopping for maintenance and water nearly as often as the coal burners they were meant to replace. For the crews assigned to the experiment, the experience was defined by uncertainty. Engineers described the turbines as whisper quiet until they failed, followed by a sudden silence and the slow realization that help would be needed. Firemen and machinists spent hours in the field, improvising repairs and waiting for relief. The promise of effortless high-speed mountain running gave way to the reality of mid-journey stalls and the embarrassment of seeing a big boy or a Challenger locomotive arrive to tow the futuristic machine back to the shop. By June 17, 1939, the demonstration was over. The turbines were returned to General Electric for further study, their brief time on the Union Pacific Main Line already overshadowed by a mounting list of mechanical failures and unscheduled rescues. In the months that followed, the mood inside Union Pacific's management shifted from hope to resignation. William Jeffers, the railroad's president, reviewed the maintenance records and crew reports, weighing the costs against the original vision. By December 1941, Union Pacific formally notified General Electric that it had no further interest in the turbine project. The experiment that began with so much optimism ended in quiet withdrawal, leaving the big boy, imperfect but reliable, as the railroad's enduring workhorse. The turbines, once hailed as the next big thing, faded quickly into the background, remembered only in the pages of test reports and the memories of those who had to pull them home. In the dry heart of the American West, water was never just another supply. It was a lifeline, and often the hardest thing to guarantee. For Union Pacific, the challenge was not only how much weight a locomotive could pull up the Wasatch grades, but how far it could go before its tanks ran dry. Steam engines like the big boy carried massive tenders, yet even those needed frequent stops. On stretches where water towers stood miles apart, every refill meant lost time and added cost. Engineers at General Electric and Union Pacific knew that if a new locomotive was to truly surpass the big boy, it had to be more than powerful. It had to survive the desert. That is why the condensing steam turbine experiment was not just about horsepower. The heart of the design was a closed-loop condenser, a system built to reclaim 80 to 90% of the exhaust steam and turn it back into usable water. Instead of venting spent steam into the air, the turbine's condenser cooled it, collected the resulting water, and cycled it back to the boiler. On paper, this meant a locomotive could run hundreds of miles through arid country, passing empty water towers that had once dictated every timetable. Water recovery became as important as tractive effort or fuel economy, an engineering priority that shaped every line of the turbine's blueprints. The aim was simple: break free from the tyranny of water stops and let a single machine conquer the mountains without waiting for a refill. This approach narrowed the challenge from brute force to endurance. The real test for the condensing turbine was not just how much it could pull, but how long it could keep moving when the landscape offered nothing but dust and distance. For a brief moment, it seemed that a new kind of survival was possible on the rails, one measured not by strength alone, but by how cleverly a machine could hold on to its most precious resource. A closed-loop condenser stood at the heart of Union Pacific's revised steam turbine vision, a technical marvel designed to recycle up to 90% of the water that once vanished as exhaust. This system, formalized and protected in U.S. Patent 2,314,819, was more than a clever blueprint. It was a direct answer to the harsh arithmetic of the western deserts, where every gallon of water saved could mean another hour on the rails. The patent diagrams reveal a dense network of finned tubes, engineered to cool spent steam back into liquid and feed it straight into the boiler. In theory, this closed-loop system would break the tyranny of water stops and let a locomotive run for hundreds of miles without pause. Yet the leap from patent office to main line proved impossible to cross. Union Pacific never built a separate, dedicated condensing test locomotive beyond the two turbine prototypes. The closed-loop system, though ingenious on paper, became a maintenance headache in practice. Condenser seals leaked, and the high-pressure piping corroded faster than crews could keep up. Each repair meant hours lost and more water added, erasing the very advantage the design promised. The engineering was sound enough to earn legal protection, but not robust enough to survive the relentless demands of real railroad work. No further condensing units followed. The concept remained a monument to creative thinking, an answer to a problem that could not be solved by invention alone. In the end, the closed-loop condenser joined the long list of railroad ideas that dazzled on the drafting table, but failed to deliver on the rails. The turbine's greatest technical refinement became another reason their future faded, leaving the big boy's old-fashioned reliability to outlast its would-be successor. Union Pacific's pursuit of the next great locomotive did not end with the withdrawal of the steam turbines. The end of World War II brought a fresh sense of possibility and urgency. Railroads everywhere faced surging freight volumes, and old solutions looked increasingly inadequate. In this environment, Union Pacific and General Electric returned to the turbine question, this time with gas, not steam, as the driving force. The ambition was unmistakable. Not another small experiment, but a full-scale fleet that would finally deliver on the promise of a single, dominant locomotive for the Mountain West. In 1954, General Electric delivered the first of 25 gas turbine electric locomotives to Union Pacific. Each one was rated at 4,500 horsepower, a figure that dwarfed most diesel locomotives of the era. The physical scale was just as staggering. With their tenders attached, these machines stretched nearly 200 feet, almost the length of a Boeing 747. Standing alongside one, a person was reduced to the scale of a child at the feet of a colossus. The turbine fleet was not built to impress the public with novelty. It was designed as a practical answer to the railroad's most punishing assignment, hauling the heaviest freight trains over the Wasatch and Sherman Hill, where grades, altitude, and distance conspired to break lesser engines. Union Pacific and General Electric placed their bet on the gas turbine's ability to deliver continuous, high-speed power. The core of each unit was a massive turbine generator, paired with electric traction motors that could drive a full-length freight train at speeds that would have been unthinkable for a steam engine. The turbines ran on bunker C oil, a thick, tar-like fuel that was cheap and plentiful in the early 1950s. Some experimental variants even burned pulverized coal, an audacious attempt to harness America's most abundant energy source for high-speed rail service. The coal-fired versions proved short-lived, but the oil-fired fleet became the backbone of Union Pacific's heavy freight operations for more than a decade. These locomotives were engineered for the vast distances and harsh conditions of the American West. Their immense tenders carried enough fuel to cross entire states without stopping. The turbine's steady, whooshing roar replaced the hammer and hiss of steam, signaling a new era of industrial power. On the timetable, their impact was immediate. Trains that once needed multiple big boys and helper engines could now be hauled by a single, unbroken string of turbine-driven horsepower. The gas turbine fleet was more than a technical marvel. It was a statement of intent, a reset after the disappointments of the 1930s, a declaration that Union Pacific would not settle for incremental gains. The railroad's leadership and General Electric's engineers were united in their belief that the future of heavy freight belonged to a machine that could outlast, outrun, and outpull anything that came before. In the scale of their ambition and the sheer mass of steel and machinery, the turbines were bigger than any prototype, bigger even than the legend they were meant to surpass. But size and power alone would not decide the outcome. The real test, as always, would come not in the design office or the pages of a trade magazine, but on the rails, where the mountains, the weather, and the relentless schedule demanded more than horsepower. The story of the gas turbine fleet would unfold in the same landscape that had humbled so many before, setting the stage for a new round of hope, challenge, and ultimately reckoning. A coal-fired turbine promises a new era of power, but inside the steel shell, the process turns self-destructive. Every ton of coal that enters the firebox brings with it more than energy. It brings ash, fine, gritty, and relentless. As the coal burns, these microscopic particles are swept along with the combustion gases straight into the heart of the turbine. Instead of clean, dry steam, the high-pressure blades are hammered by a storm of abrasive dust. The effect is slow at first, almost invisible, but over weeks and months, the damage becomes impossible to ignore. Maintenance logs from 1962 and 1963 show turbine blades losing about 1/10 of an inch of metal for every 1,000 hours of operation. Each pass of the ash-laden steam scours the blade surfaces, rounding off the carefully shaped edges that once sliced the air with precision. The designers had hoped for a 5,000-hour interval between major overhauls, a schedule that would have made the turbine competitive with any diesel or steam engine. Instead, the real-world numbers collapsed to barely 1,200 hours. For the crews tasked with keeping the turbines running, the math is brutal. Instead of months between major interventions, the locomotives are pulled from service every few weeks. The high-pressure turbine stage, where the steam is hottest and the ash most concentrated, becomes the primary point of failure. Worn blades mean less efficient energy transfer, which in turn means higher fuel consumption and lower pulling power. As the hours tick by, the turbine's output drops, and the once promised efficiency is lost to friction and heat. In the shops, maintenance teams face a battle they cannot win. Blade sets must be replaced or rebuilt far more often than planned. Each overhaul is expensive, labor-intensive, and time-consuming. The turbine's supposed advantage, its smooth, continuous power, turns out to be its greatest vulnerability. The very fuel that made the experiment practical on paper is what kills it in practice. The consequences ripple outward. Every unscheduled repair means a train delayed, a schedule missed, a crew stranded. The economic model that justified the turbine's existence, long intervals between service, high reliability, lower operating costs, disintegrates under the weight of constant breakdowns. The railroad's hope for a coal-fired revolution is undone by a flaw that no amount of engineering finesse can erase. Coal ash is simply too abrasive for the delicate internals of a high-speed turbine. The final verdict comes not in the boardroom or the design office, but in the maintenance bays and on the shop floor. The turbine that was supposed to end the age of the big boy cannot survive its own appetite. The experiment eats itself from the inside, leaving behind only worn metal, exhausted crews, and a lesson as hard as the Wasatch granite. In the world of heavy rail, reliability is the only power that matters. In the late 1940s, Union Pacific's turbine gamble rested on a single, seductive number: the price of bunker C oil. Refineries flush with post-war surplus sold this heavy, dirty fuel at a deep discount, $1.50 per million BTU. Accountants ran the math. Turbines, burning thousands of gallons per run, could outmuscle anything on rails if fuel stayed cheap. Internal memos from those years show a confidence built on abundance. Coal was still inexpensive, diesel fuel only beginning its slow ascent, and the raw cost per horsepower hour made the turbine look like a sound bed. For a moment, the numbers worked, but the world changed. By 1952, oil prices began to climb, slowly at first, then with a jolt. The Suez Crisis in 1957 sent shockwaves through global markets, pushing the price of bunker C to over $3 a barrel. Suddenly, what had been a waste product became a commodity. Through the early 1960s, costs kept rising. By 1965, bunker C reached $10 per million BTU, over 6 times its original price. Every spike landed squarely on the railroad's balance sheet. The turbine's economic advantage vanished, replaced by a growing liability with every fuel delivery. Union Pacific's own filings to the Interstate Commerce Commission captured this reversal. Cost reviews from the mid-1960s compared turbine electric and diesel electric power, line by line. The verdict was unmistakable. Diesel electrics, once the fallback, now offered a lower fuel cost per ton mile. Turbines burned nearly a pound of bunker C per horsepower hour. Diesels used less than half that with number 2 diesel oil. As energy markets punished heavy oil, the cost gap widened. The turbine's supposed edge dissolved into red ink. Fuel costs told only part of the story. Diesel electrics brought a new standard: reliability. Maintenance records showed diesel units running more than 7,000 hours between failures. Turbines battered by ash and heat rarely reached 1,200 hours. Diesel locomotives did not require specialized crews or exotic parts. They could be serviced anywhere along the line, from Omaha to Ogden. Their engines started in winter, ran on fuel available at any depot, and shrugged off the price swings that crippled turbine economics. When a diesel failed, it could be swapped out in minutes. Trains kept moving. Schedules held, and the railroad's promise to shippers stayed intact. By 1968, Union Pacific's own numbers showed turbine operation cost 25% more per ton mile than diesel. The turbine fleet, once the pride of post-war ambition, had become an economic trap. Every hour a turbine ran, it lost money that horsepower alone could not recover. The final decision fell to accountants and dispatchers. The diesel-electric did not promise spectacle, but it fit the work. Reliable, adaptable, and affordable, it became the new standard. The turbine, for all its promise, could not match a machine that simply worked. The end came quietly. In August 1968, the last turbine locomotive left the main line, its final run unheralded and unremembered by the crowds that once gathered for the big boy. There was no ceremony, no farewell in the press. Just a line in the operating ledger, another machine retired. By 1970, Union Pacific formally removed the entire turbine fleet from service. Within 2 years, every unit was gone, cut apart in the scrapyards, their hulking frames reduced to piles of steel. Not a single turbine locomotive was preserved. No museum display, no commemorative plaque, no engine tucked away for future generations. Inside Union Pacific's files, the decision was blunt. Internal memos dismissed the turbines as lacking historical or public interest value. The scrap price outweighed any thought of preservation. For the archivists and company officials who made the call, these machines were failed experiments, not heritage. The paperwork closed the chapter, and the turbines disappeared almost as if they had never existed. Meanwhile, the big boy, an engine built as a last stand for steam, endured. 8 of the original 25 were saved, their enormous frames restored and displayed across the country. Decades after their last revenue run, big boys still draw crowds, their legend growing with each passing year. They became symbols of American engineering, the very image of railroad power. The contrast is stark. The turbines, once imagined as the future, left behind no physical trace. Their story survives only in faded photographs, technical papers, and the memories of a few who worked on them. The locomotive designed to end the age of the big boy was itself erased, while the so-called obsolete giant became immortal. In the end, it was not the promise of power or innovation that lasted, but the reliability and familiarity of a machine that simply did its job. The turbine's quiet disappearance is a reminder that history remembers what works and forgets what does not. The great irony endures. The mighty big boy, built to be surpassed, became immortal, while its high-tech challengers faded into scrap and silence. Today, railroads still prize what the turbines could never deliver: unwavering reliability, not just raw muscle. In every field chasing the next revolution, history reminds us, the future belongs not to the boldest blueprint, but to what endures when dreams meet the rails of reality. Thanks for riding through this forgotten chapter with us.